Hey everybody, it's Ripley back again. So what we're going to talk about today is the calculus of polar functions. So by the time you're done with this lesson, you should be able to take a derivative of a polar function, meaning you should be able to find the slope and equation for a tangent line in rectangular coordinates from a polar function. You should also be able to integrate, find area between, under, air quotes, under a curve. And you should be able to figure out arc length of a polar function. All right, so those are the three things that we want to get done. But let's just not get too crazy. Let's start with a function. Let's do r is equal to 5 cosine of theta. Let's go plus 2. Now, I've already got it graphed up, sort of Cooking showed it over here on my graphing calculator. So let's take a gander at what this thing is. So 5 cos theta plus 2. Just for a second, can you see what this thing is? Is it going to be a limaçon? Is it going to be a cardioid? What's it going to be? All right, let's take a look at the graph. Maybe you hit pause and you can guess or not. And pow, here it is. All right, now how does 5 cos theta plus 2 make this thing? Well, let's look really closely. When theta equals 0, so 5 cos theta plus 2. When theta equals 0, cosine is 1, so 5 times 1 plus 2 is 7. So it starts here, right? And then it curves around. Now at pi halves, think about what 5 cos theta is, right? Let's go back over here. Just build a quick down and dirty. This is going to be r and theta. So just a quick little coordinate tree. When this is theta, we know this is 7. When this is pi halves, cosine of pi halves is 0, so this is going to be 2. When this is pi, now when it's pi, cos is -1, isn't it? Which would give us -3. When it's 3 pi halves, cosine's back to 0, so we get 2. And then at 2 pi, we're right back where we started, back at 7. So it should carve the whole thing out, excuse me, in 2 pi. But let's look. All right, let's see. At 0, we're at 7. At pi halves, at pi halves, we're at 2, just where we want it to be, right? At pi, now this is where it gets weird. Remember, that gave us a -3, so as we crank around, from pi halves to pi, we carve out this entire part to here. Excuse me, at 3 pi halves, so from pi to 3 pi halves, we carve out this entire part, so this part of the curve. And then from 3 pi halves to 2 pi, we grab this part of the curve. Okay? All right, so we know what this thing looks like. So what we're going to do first is we're going to figure out, let's find the derivative at any point. And you may say, well, Ripley, how the heck are we going to do that? We've got this strange, I want to figure out the derivative. I'm going to draw it horribly, so bear with me. I've got... Oh, that's awful. I want to figure out the equation of the line tangent at some point, right, on this curve. Let's say at theta equals, let's say it's pi thirds, shall we? It'll keep it simple. I know it doesn't look like pi thirds, but give me a break, would you? So I guess pi thirds, I'm being a little bit lazy. Pi thirds would be about there, wouldn't it? So that guy right there is going to be theta equals pi thirds. And we'll get rid of this just because I was being a little lazy. I'm sorry. Now, I don't really know what point that is, right? And if I'm going to find the equation of a line tangent in polar form, or excuse me, in rectangular form, I kind of need to know the point. So remember, x is equal to r cos theta, right? And y is equal to r sine of theta. True? So I need a point. So the first thing that I'm going to do is I'm going to find, I know what theta is. So I know that x is going to be equal to 5 cos pi thirds plus 2. I'm just plugging it into r, right? Times the cosine of theta, which is 1/2. And y is going to equal 5 cosine of pi thirds plus 2 times the sine of theta, which is √3/2. So what's that equal? Cosine of pi thirds is 1/2, so 5 halves plus 4 halves, which is 2, is 9 halves times 1/2 is 9 fourths, right? Let's see, likewise here we got, what do we end up with here? 5 halves, 4, 9 halves, so 9√3/4. So y is going to be 9√3/4. Now I have my point. Now I need my slope. Well, remember that slope is equal to dy over dx. Well, what am I going to do here, right? Well, except, look, I know that x equals r cos theta, and I know that y equals r sine theta. So couldn't I rewrite this as dy over d theta, remember our little, it's kind of like chain rule, right? Whoops, over dx over d theta, over dx over d theta. Now, how do we manufacture this dy over d theta and this dx over d theta? Well, I've got an r right here. So if I were simply to multiply through this guy through by cos theta, wouldn't that give me r cos theta is equal to, what would that be? 5 cos squared theta plus 2 cos theta. True? And remember, this is x of theta now. I know that y of theta similarly is going to be r sine theta, right? Which is equal to 5 sine theta cos theta plus 2 sine theta, right? Now, I know that dy over d theta, so dy over d theta is just the derivative of these guys. Well, really just the derivative of this, which is 5 cos theta by product rule. So it's 5 cos theta times cos theta, which is cos squared theta, minus 5 sine squared theta, again, just by product rule, plus 2 cosine of theta. So, ooh, this could be ugly. dy over d theta at theta equals pi thirds is going to be, let's see, theta equals pi thirds is going to equal 5 times cosine. It's too early in the morning for me to try and figure this out. 5/4 minus 5 times 3/4. Ooh, that's not so bad. Plus 1, right? Because cosine of pi thirds is a half, 2 times. And we're good. All right, so good Lord, what does this turn into? 5/4 minus 15/4, got to be nicer, plus 4/4. Is negative 10 is equal, oh, that's not bad, is equal to negative 3/2, right? So that's dy over d theta. Now I have to find dx over d theta. Do the same thing. So dx over d theta is equal to, I got to be careful here, this is going to be 10 cos theta times negative sine of theta, right? That's just blah squared that we got to be careful of, minus 2 sine of theta, right? Everybody buys what I'm selling, minus 2. Yeah, because I'm good. So dx over d theta at theta equals pi thirds is going to be, again, a half. So this is going to be 5 times negative root 3 over 2 minus root 3, right? Because that's going to be root 3 over 2. Yep, those cancel. So this is going to be root 3. So this is going to be, what's that going to be? Negative 5/2 root 3 minus 2/2 is negative 7/2 root 3. So all I have to do is take dy over d theta over dx over d theta, and I get my m. So m is equal to dy over d theta, negative 3/2. I hope I didn't make a mistake on that. I could have. You guys know me. Over negative 7 over 2 root 3. Cancel, cancel. Those guys cancel, and this becomes negative, what, 3 over 7 root 3, doesn't it? There's my slope. So now you may be going, whoa, Ripley, what? That's ugly. Well, who cares? Remember, as long as we have a point, whoop, and a slope, we have a line. So if I go y minus 9 root 3 over 4 is equal to negative 3 over 7 root 3 times x minus 9/4, we're good. Which kind of, I mean, my drawing is terrible, but you can see it a little bit better here. At pi thirds, right, pi thirds, this thing's going to be a little bit negative. Now I squared this off, so it kind of looks, pi thirds feels kind of strange in terms of where it's at, but this guy's going to be, it appears that it's going to be just a little bit negative right there, okay? All right, so that's how you do slopes of lines, tangents, derivatives, all that good stuff with polar functions. I'm going to meet you guys on the next page, and we'll actually do areas with polar functions or polar equations, which is really cool. I'll see you in just a second. One real quick error that I want to talk to you guys about. Like a dingus, I forgot to cross this off which would make this positive, which would make this positive, which would make it make a lot more sense when we take a gander at our curve, right? Because pi thirds, ooh, look, I put in pi thirds. This is clearly going to have a positive slope. Respect thy negative, Ripley. Okay, whoops, I don't know why I did that. Let's go ahead and go back over here. Let's talk about areas now. So same curve. R is equal to 5 cos theta plus 2. All right, so take a gander at this thing. Now, this is going to be a little bit tricky. What I want to do is I want to figure out the area of the curve between here and let's figure out the area of the top half. So everything above the x-axis, excuse me, but excluding this loop, okay? I want to remove this loop. So in other words, let's go back to my curve. Let's go back here. Let me draw it really quickly and really poorly. So what I want to do is I want to figure out the area of that part right there before this thing whips around. So what I want you to think about this as, the easiest way to think about this is to think about it as a Japanese hand fan. You know what a Japanese hand fan is, right? So what we're doing is we're opening up this hand fan like this. Now, it's a goofy looking hand fan, I realize. But what we're doing is we're creating little slices of area as we open up. As theta grows, we get all of these little areas, right? Now, before this thing whips around, we'll talk about the ramifications of that because we can get ourselves into a lot of trouble. Before we talk about what happens as this thing whips around, let's just think about how to find these little slices of area. Now, if you recall, when we had a regular function, what do? And we're trying to find the area under the curve. This is f of x, and I'm trying to find the integral from a to b. This is just awful. What did I do? I built rectangles, didn't I? Remember, I could either do an RRAM or an MRAM and build myself little rectangles. That's not going to work for this because we don't have that kind of function. It doesn't make any sense. Well, if you think about one of these little slices right here, this looks very much like, let me change colors one more time, like the sector of a circle. And really, that's how polars are created, right? They're little sectors of circles. Remember, if I've got a circle, if you recall from your trig days, not a bad circle right there. A sector is that little pizza slice, right? Or excuse me, a segment. I just said sector. The sector is the crust. The segment of a circle. Now, if you recall, excuse me, the area of that sector, or of that segment, I keep doing that, area of a segment is what? Well, hopefully you remember it was 1/2 r squared theta, if I have a central angle right here of theta. That's the area of the segment. Now, how is this area, if I were to zoom in, it would look kind of like this segment. Well, how is this segment created? Well, I've got a fixed r, so we would call this r sub I, right? This is my fixed r, and then I carve out, just like opening a hand fan, that little segment. Now you say, but Ripley, the r changes. Well, yeah, remember though, our height changed here, and we just used a rectangle. It's this big clunky thing. Then we took the limit, and we let the number of these subintervals, these rectangles of these specific widths, go to infinity, and I got the exact area. Well, I do the exact same thing under here. The question is, what's this theta? Well, that's easy. This guy's just delta theta. Now, I'm going to change colors. Let's do orange. Remember this. When I let the number of subintervals go to infinity, what I got was a series of infinitely thin rectangles, right? And it filled in the area perfectly. That's not bad. We're going to get exactly the same thing if I let the number of these little segments go to infinity. We fill in the exact area, right? So think about that. All I'm doing is I take the limit as n goes to infinity of the sum as I goes from 1 to n, just like before, of 1/2 r sub I squared delta theta. That's all I do. And this is equal to the integral as theta goes from a to b of 1/2 r squared d theta, right? Remember, as I take the limit as n goes to infinity, delta theta becomes d theta, which is magnificent, right? It's so easy to deal with. Now, so let's go back and try and figure out the exact area of this guy. I want the area, quote unquote, under the curve, even though this cannot be defined as a function itself, can it? We have a function of x like this, so we can't really call it a function of x in the traditional rectangular sense. We have to call it r of theta. Well, I'm kind of liking this deal. Now, think about this. I know that this point, I gotta change back to black. I know that this point right here is when theta equals 0, right? When theta equals 0, this is the point 0, 7. But if we want to do it as r theta, that's where it gets confusing, isn't it? Whoops, 0, 7, what am I talking about? This is 7, 0, right? So I've got 7, 0. As you notice, it's real easy to get confused with this, so we got to be a bit careful. Now the question is where does this thing stop? Well, I wanted it right where it comes back to the origin. Well, it comes back to the origin when what? Well, when r is 0. So if I'm trying to find the limits on this, all I'm going to do is I'm going to let r equal 0. So when 0 equals 5 cosine of theta plus 2, or when cosine of theta equals -2/5, or when theta equals the inverse cos, or arc cosine of -2/5. Now we know that the whole thing wrapped around when theta equaled pi. So when I solve for this, I better have it in my brain. Don't let the idiot box do all the work for you. I better have it in my brain that it happened somewhere between pi halves. When this thing was pi halves, I know that r was 2. So somewhere between pi halves and pi. Let's go back to our handy dandy calculator here. I'm going to solve this in both ways. I'm going to take the inverse cos. Let's see what mode we're in. Come on, mode me. We're in polar. Let's see, I want radian. Okay, we'll go radians first. So second quit, and we're going to go inverse cos of -2/5, or -0.4, right? -0.4, and paren, boom, let's see what we get. 1.98. Now let's change the mode. We'll change it to degree real quick, just to make sure I know what I'm talking about here. Hit enter, second quit, second inverse cos of -0.4, and paren, and enter. 113 degrees, just like we thought, which is 1.98, we'll call it 1.982. Now here's the coolest part, watch. When I want to find the area under that curve, I simply go, so the area, let's change to orange again so we know what we're talking about. I take the area under that curve is equal to the integral, what did I say that was? 1.982. So this is going to be the integral from 0 to 1.982 of 1/2. Now, it's r squared d theta. So I simply have to go 5 cosine of theta plus 2 squared d theta. Now, if I had to do this by hand, I totally could, right? I could multiply this thing out. I could do all my trigonometric tricks, and I would get a value. Right? It would be a pain in the butt because I'd have that cos squared, and then I'd have a 10 cos theta, and then I have a plus 4, which isn't too bad, right? But I'm going to do it with my calculator. You might see that you pull this half out, which sometimes is fabulous, though. Sometimes you don't want to do it because it'll cancel in terms with this depending on the function, the polar function. So let's crank it in our calculator really quick. Go back here. I'm going to go math. I'm going to go 9. I'm going to go 0. What I say? 1.982. Right? 1.982. Now you guys know I hate decimals, but when you're dealing with this, when you're dealing with your integral, sometimes it's just easier. And then what did I have? I had 5. I got to do 5 cos theta in paren plus 2 in paren. Square that sucker. Boom, and then d theta. Stick my theta in here. I'm going to hit enter, and life is good. Looks like I got 48. All right, so this is 48.545 units. Now, those are still, you can think of them as rectangular units. What did I, give me that again? 48.545. So approximately equal to 48 48.545. In other words, if you added up all these little squares in here, there would be about 48.545 of them. In other words, there's nothing crazy about this. I don't have to convert this into thetas or r's. It's just rectangular units. So that's how it works. So simple. All right? The only thing that you really have to remember is this. The hard part is dealing with the thetas. Now, why is that? Well, let's say that I change the problem a little bit. Now, I'm going to try and draw this thing one more time, but I'm going to draw the whole thing. All right? And you know I'm going to draw it poorly, so don't be jerks. So here we go. Oh, that's not bad. Oh, that was terrible. All right. Sorry. Oh, I'm such a terrible artist. I apologize. Just wait till Calc 3. You're really going to laugh at me. Now let's say that I'm not actually going to do the whole thing. We're just going to set it up. Now let's say that I wanted to find that area right there. Now there are some tricks here. I know that the whole area, if I wanted to include this little loop-de-doop-de, right, then I would simply go from 0 to 1.982. So what I'm going to do is I'm going to think about this for just a sec. I want to find just the red area though. So let's change to blue and let's set this thing up. You're probably seeing that what I'm going to do is I'm going to take the integral from 0 to 1.982 of 1/2 times 5 cos theta plus 2 squared d theta. And then you're going to say, but Ripley, that's too much. Well, we're not afraid. Watch. We'll just subtract out this chunk in here. Now you may notice by symmetry arguments that you learned back in pre-calculus that this chunk, even though I've drawn it horribly, and this chunk right here are exactly the same. Now since we're talking about areas here, I can integrate from 1.982 to pi. Remember that was about 113 degrees. So I can integrate from here to here and it will give me all of that area. Notice if we think of it again like a Japanese hand fan, what I'm doing is I'm carving all of that out. Since these two are equal, I don't have to go from pi to whatever pi minus 1.982 is, or plus the difference, right? It becomes sort of a trigonometric just brain cramp, all right? Because of symmetry, I can make my life easier. So I simply do exactly the same thing. I go 1/2 5 cos theta plus 2 that guy squared d theta, which is fantastic. Now, let's make sure that, I'll prove to you, you might say, but Ripley, wait a sec, isn't this going to be negative? No, because I'm carving out positive area. And since this area and this area are the same, it's okay for me to subtract them. Now watch. Okay, you guys, sorry for the abrupt cut, but something about this integral right here, this guy, was bugging me. And if you're following along, it probably confused you as well. I just had this little thought, did I change back to radians when I went to degrees? Because that seemed just a little bit too big based on the curve. So remember our graph, that's this guy right here. I was like, wait, 48 is too big. So what I did is I reran it real quick and I got 23.227. And the problem is, the reason I got the 48 is because I'm a ding dong and I forgot to convert it back to radians. So this should not be 48.545. This should be 23.227. So 23.227. This, let's see, I don't know what the heck that is. Let's get rid of that. If I go back to here, let's see, I want to go back here, and I actually put this one in as well. So if I hit second entry and second entry, let's see, because I really would prefer not to put this whole thing back. This is kind of a pain in the butt. And it's a drag, but it's easier than having to put the whole thing back in this case, just to make sure that I go from 1.982 to pi. I did. Outstanding. So if I hit enter, now we're back in some numbers that make some sense. So 2.690. So we know this guy is going to be approximately 2.690. So if I want the area of just, whoops, let's change colors, of just the red stuff right here, remember I integrated from 0 to 1.982, that gave me this number. Then I integrated from 1.982 to pi, that gave me this guy. So if I want the area, then this, let's come down here, this is equal to 23.227 minus 2.690, right? What is that? 221, 20.53, what is that? Like this is tricky to do. 7, 3, 5, whoa, what's going on here? 11, yeah, 5, right? 20.537, is that right? That looks about right. We'll call it good. So this is approximately equal to that. All right, enough of the arithmetic. So hopefully you get the gist of how this integration thing works. Now I will tell you that in class and on the assignment, you're going to be working with like areas between curves where like I'll have this guy and then I'll have a circle over here and I want the area in between. Well, just think about it the same way. Just build it geometrically, build it from a polar standpoint. And it shouldn't be too bad. In the interest of keeping this video way under like 7 hours, I'm not going to do that. We'll play around with that in class. Just remember, the most important thing is there's our formula, and then just remember how these areas open up like Japanese hand fans. All right, I'll meet you back in the last section. We'll talk about arc length, so lengths of polar arcs, and then we will be done. All right, see. Okay, one last quick little thing. If you recall that the length, I don't know why I'm doing this in red, let's do this in black, that the length of an arc can be written as the integral from a to b of the square root of dy over dt plus dx over dt. Of course, both of these are squared, right? And this is dt. Now, it shouldn't be these limits are on t. It shouldn't be a huge reach for you to see that if I just use a different parameter instead of t, use theta, I can easily write this as dy over d theta squared plus dx over d theta squared d theta, and this will be from theta equals a to theta equals b. However, remember, we've got an arc, what was it? R equals 5 cos theta plus 2. The problem is this doesn't make a whole lot of sense. However, I'm going to show you something that's kind of fun. I'm going to show you how to find the length of any arc on this thing using this equation, but without having to go through too much god-awful monstrosity. I'm going to show you a shortcut because we could just as easily find, remember back when we found dy over d theta, like these guys over here, dy over d theta, I could find this, right, square it, and then plug it in, but that can get out of hand really, really quickly. So I'm going to show you something that's kind of cool. We know that x equals r cos theta, and we know that y is equal to r sine theta. Okay? However, we got to remember that these r's are really just functions of theta, right? This is just functions of theta. All right, same thing. So I know that dx over d theta can be written if we want it to, but if I use product property, this would be dr over d theta, right? Because this is implicit differentiation, cos theta minus r sine theta, right? And then similarly, I know that dy over d theta would be equal to dr over d theta. In other words, the derivative of r with respect to theta, remember this is our little key term there because it doesn't have a theta in it. It's 1 dr d theta through implicit differentiation. Sine of theta plus r cos theta. Now, don't get too impatient with me here real quick. Remember, these are both going to be squared. So dx over d theta squared is equal to, what the heck is it equal to? It's equal to dr over d theta squared cos squared theta minus, and then this is going to be 2r dr over d theta sine theta cos theta, slow your brain down, plus r squared sine squared theta. Similarly, dy over d theta squared is equal to dr over d theta squared sine squared theta plus 2r dr over d theta, sorry, sine theta cos theta. That's kind of convenient, isn't it? Notice how I lined them up. I'm so smart. Cos theta, and then plus r squared cos squared theta. Now, hopefully you notice those guys are going to cancel. That's going to be awesome, right? And then this guy right here is, I can factor out dr over d theta squared, right? And then I'll get a sine squared plus cos squared, which is 1. So this turns into dr. By the way, right now what I'm doing is I'm adding them, because why am I adding them? Because that's what goes right here. So this becomes dr over d theta squared, and then look at what happens here. I take r squared, factor it out, sine squared plus cos squared is 1, and I get plus r squared. Isn't that pretty cool? Now remember, r is a function of theta, so this guy would just be the integral from a to b of the square root of r squared plus dr over d theta squared d theta, which is pretty cool. We could plug it, chug it in, we can use our calculators to do it, we can grind it out by hand, but that's a pretty cool little formula. Remember again that these are limits on theta, and now you have it. So if I wanted to figure out the integral from, so what would I do? Let's stop. We're not going to go through the whole thing because you guys will go insane, but what was it? From the arc length from theta equals 0 to theta equals what, pi halves, right? So if I go back to my curve, that would be from here to here, and I just plug and chug it in. What do I need? I got r, so this would equal the integral from 0 to pi halves. I got r, so this would be 5 cos theta plus 2 squared. Sorry about that. Let's erase this guy. I know dr over d theta is just what? Negative 5 sine theta. So this would be plus negative 5 sine theta squared, and then d theta, and I'm done. Whatever this number is that it equals. And that's it. It's kind of fun. So now we know how to basically convert, go back and forth between polar functions and tangent lines in the Cartesian plane, so using rectangular coordinates. We can find areas of curves of polar functions, and now we can find arc lengths. We basically got everything. All of calculus, derivatives, integrals, and then this arc length thingy ding. All right, cool. Thanks for your time and attention. I'll see you in class tomorrow, and have a good day.